All right, so we've been looking at reactions and different types of reactions we can start to see. Now we're going to look specifically at some gas-forming reactions and how we can start to get some bubbles coming up. There's a lot of these types that we've kind of discovered over the course of chemistry and our chemical history. That's because they're really easy to observe. We can take two things, put them together. Do we get bubbles? If we do, what could be potentially making those gas particles? And so we're going to look at a bunch of these. Just really worth noting because this is going to key us into start to be thinking about, okay, are we actually going to make a gas based on the reactants that I've put together? It's just another tool for us to be able to start to predict what it is we're making. Cool. I'm going to hop on over so I can, tech stuff. All right, so let's get going with this first one here. We got an acid plus a carbonate or an acid plus a sulfate. Hopefully, as we're looking here, we can start to think about what these, because these are the special things, right? These are the special particles, the carbonate or the sulfate, what these might want to form. Well, they're going to try to form, as we think about what it is they're going to make, they're going to try to form one of two things. The carbonate is going to try to form this very stable carbon dioxide molecule, a bunch of it in the air, right? And your sulfites are going to try to form our sulfur dioxide. And so as we think about these two types of particles, here's what they're going to try to make. Because the acid could be anything, right? Just anything that starts with a hydrogen. But the key here is carbonates are going to go to CO2. Sulfites will go to SO2. Cool. Let's look at an example here. We've got our sodium carbonate. Sodium is a 1+. Carbonate is CO3 2-. So we're going to need 2 of those sodiums. This could be a solid. This could be an aqueous. Oh, it does tell us it's an aqueous solution. Cool. Good to review some of our state symbols here. Hydrochloric acid is going to be HCl, also aqueous. Again, we're not doing any net ionics yet. We're just kind of looking at our reaction archetypes. Cool. We know the CO3 is going to break apart into CO2 is what's going to happen here. Cool. What else do we have to work with? Well, that leaves us an oxygen coming off of that carbonate, right? Well, that's going to get with the hydrogen from the acid to make a stable compound. That's going to be our H2O. So now we've used the hydrogens and the other oxygen. We've used the carbon and 2 oxygens. What do we have left? Well, we got some sodiums and we got some chlorines. Well, that's going to make our sodium chloride for our last piece here. So water, salt, and our CO2. The one we're going to see visibly is that gas. We're not really going to see the water form. And the salt we're not going to see because that's going to be an aqueous solution. Sorry, that was a little hard to read. CO2 gas, H2O liquid, and NaCl aqueous. Cool. Just an example here as we start to think about our reactions, what we could see for our carbon dioxide or sulfur dioxide gases. Next example here is our acid plus a hydrocarbonate or a bicarbonate species. Good news, it's the same gas. We're still making CO2. It's just going to make balancing easier. Also, oh, nobody said it. Well, maybe you said it, but we didn't balance that last one, did we? Womp, womp. That is a violation of the law of conservation of mass. We've got 2 sodiums. Let's go back. Let's fix it. We got 2 sodiums here on the front side. So we're going to need 2 on the back. Sorry, let me undo that. So we're going to need 2 here. That gives us 2 chlorines. So we're going to need 2 of our hydrochlorics. I've got 2 hydrogen there, and then I've got 2 hydrogen in my water molecule. Cool. Should check out then for our balance. Cool. Another example here. So sodium bicarbonate just indicates to us that there's an extra hydrogen in there. So we're going to have NaHCO3, and that's also a solution, plus our hydrochloric, HCl, also an aqueous. Come on. Come on, pen, don't fail me now. AQ. We're going to have the same gas produced. We're going to make some CO2 gas. That's coming from that carbonate. One of the O's is going to get together with this hydrogen. Oh, and there's another hydrogen to make our water. And that's going to be a liquid. Ooh, we're going to have enough space. Let's see if I can get in there. And we've got our leftover NaCl again. NaCl, and that's going to be aqueous. Sorry, that's aqueous. Kind of squeezing it in there. What's nice here is because we have that extra hydrogen, we're balanced. We don't have to do anything for this one. It's all 1s for our coefficients as we're going across. Cool. I'll start the next one over a little further so we can have enough room to see a little more clearly. Cool. Strong base plus ammonium. Here, the specific molecule or diatomic that we're looking for is the ammonium. Ammonium really wants to go to ammonia gas. So anytime you see that ammonia molecule with a presence of a base, we're going to end up with ammonia gas is our bubbles that would come off. And you would know this. It's going to stink. Ammonia is that kind of bleachy, cleaner smell that we sometimes will smell. Ammonium chloride is NH4Cl, NH41+, Cl1 minus, and we're good. Plus potassium hydroxide, KOH. Don't have enough quite for state symbols here. This first one could be aqueous or solid. We don't know. Most likely the base is an aqueous solution, but again, we don't know. Could be a solid. Be unlikely, but could be done. Cool. If we think about what's going to happen here, active particle of base is at OH. For our ammonium to turn into ammonia, it's got to get rid of one of these hydrogens. Got to get rid of one of these hydrogens. If it does that, it turns into NH3. There's our gas. That leaves one hydrogen and an OH. Oh, there's our very stable water. We know that wants to make in a liquid state. And then our leftover bits here, we've got potassium and a chlorine. We get a potassium chloride salt formed, which is going to be aqueous in that water solution. Cool. Again, we're looking specifically at our gas molecules. So here our gas is at NH3 gas, the ammonia gas. We had CO2 and CO2 for the other two examples up above. So just thinking about what we're going to be making as we start to have our gas produced. Cool. Next example here is an acid plus a sulfide. Well, what's the active particle of an acid? It's an H. So an H is going to get with the S2 minus to make H2. Whoa, sorry. H2. Come on, undo. H2S, which is our hydrogen sulfide gas. This one's fun. Yeah, we're going to make acidic gas. Great. It makes a gas. Our example here is our sodium sulfide, Na2S, is reacting with acetic acid, which is HC2H3O2. Sometimes you'll see that written slightly different where it's the CH3COOH. That's just kind of a hybrid of its structural formula. The H gets with the S to make H2S. H2S, and our leftover bits here are going to be the NaC2H3O2 as a salt. If we're looking here, sorry, I'm falling off of my state symbols. We just lost information to be able to know what our state symbols are. If we're looking, we got two sodiums on the reactant side. We only have one on the product side, which means we're going to need a coefficient of 2. That makes 2 of the acetate ions. So we're going to need 2 acids. That makes 2 hydrogens to balance our reaction. Cool. So our gas here, again, the important species that we're trying to make or should be keyed into is that hydrogen sulfide molecule. Cool. This next one's real fun. So cyanide, which is a poison, again, reacting with an acid, which is going to have that H out in front. That's going to form a hydrogen cyanide gas. Cool. Not only is it an acid gas, but it's a poison acid gas. That's fun. Cool. This one's pretty straightforward. Sodium cyanide would be NaCN. With our HCl. That's going to go ahead and form for us our hydrogen cyanide gas. That uses the H and the CN, leaves behind our NaCl. So this is a double displacement reaction if we're thinking about our reaction archetypes. Acid plus a metal, you've seen this before. Acid plus a metal makes hydrogen gas. We've done this one a couple times in the lab. Magnesium metal plus some hydrochloric, HCl. This is a single displacement reaction. That magnesium kicks out the hydrogen to make our hydrogen gas. It takes the place in that compound of our MgCl2. And then to balance, we would need 2 of those acid molecules. Excuse me. Cool. This last one here is new for us, but really it's kind of nice because all we're doing is we're drying it and then we're breaking it down. So a hydrate is a molecule that has water molecules loosely attached to it. So it's like when we form ionic crystals here on Earth, because there's moisture in the air, sometimes those water molecules get trapped in the crystal. As a result, there's water molecules that could be driven off, which then affects the molar mass or the mass of the particle. So if you took, for lack of a better term, if you took a wet towel and you put it in a dryer, the first time you heat it, it just dries the species. It just dries it. So you just end up with what we call an anhydrous salt, or a dry salt, anhydrous, or without water. The second time you heat it, then it actually starts to decompose. You actually split apart now this ionic crystal or ionic species. So for example, we've got this calcium sulfate heptahydrate, CaSO4 is, try to write a little nicer for you. CaSO4, and that heptahydrate tells us how many water molecules are attached. And so we just kind of show that as there's a dot, we're saying it's loosely attached. Hepta means 7 H2Os. And there's our calcium sulfate heptahydrate. The first time we heat this, all we do is we split it apart. We end up with CaSO4 now as its own solid species, crystal, and then we're going to drive off 7 H2Os. Ooh, get it in there. All right. Usually in the form of a gas. We drive it off as steam. And I know what you're thinking. Those look like they're the same thing. The only difference is kind of the symbol. This little dot tells us it's loosely attached. Here we're now saying it's two separate things. If we were to then take this calcium sulfate, let me wipe real quick. We then take the now just alone calcium sulfate and heat it some more. If we heat it enough, it actually splits apart. We will actually break apart into a smaller species. In this case, it would be calcium oxide as a solid. We would drive off a new gas of SO3, sulfur trioxide gas. You could argue that the sulfur and the oxygen flip-flop here a little bit. You could say, oh, we make 2 oxygen molecules in calcium sulfide. Electronegativity will actually tell us that the oxygen is more likely to keep a hold of those electrons, but either one of them are kind of justifiable, and it's actually going to depend on how much heat gets applied in the drying process. But, cool, just some specific or some different reaction archetypes that we should be on the lookout for when we start to think about the reactions that might take place in our beaker.